Okay, welcome back to our second of 3 introductory workshops on getting going with R. So it's good to be back, and we'll just jump right into it. As we did yesterday, the format of our workshop today for the next 90 minutes will be some slides, then we'll go into an exercise in RStudio Cloud, and then some more slides, and just like we did yesterday. So like yesterday, hopefully this will be mostly hands-on, like more than half of the time spent actually doing some exercises. But we'll keep going with what we covered yesterday, and we'll start out with a little bit of a review from yesterday. So let me go ahead and go to our little slide deck here. So I'll put the URL for our slides in the chat window, just for convenience. They will be up here for a long time. Recordings will be posted probably next week. I don't think I'll get to it by Friday. All right. So what we're going to look at today is working with packages and the functions that you get from packages. And then that will be leading up to using piping syntax, which is going to come in real handy when we do data wrangling on Friday, and then importing data. So we're moving towards actually importing some data and getting it ready for statistical analysis. We won't get the whole pipeline this week, but we're going to get you through that part of it. Okay, we got the recording going. That's my little sticky note. Okay, but let's begin with some review of what we did yesterday, right? So the first thing we did was we fired up RStudio, and we learned that we can simply type in expressions at the console, hit enter, and essentially use it as a fancy calculator, similar to what you could do with Excel, right? So that's good. It's got lots and lots of powerful functions, but we can get a lot more mileage out of R for a programming environment if we save the values of those expressions to objects or variables. Okay, and we can use the equal sign to do that. That's a standard feature of all programming languages, is that you can save results to things. But to remember that every time you create an object, it has a class. You usually don't have control over what the class is, but you can definitely see what the class is by using that class function. We also talked about another powerful thing that R provides is that out of the box, pretty much all of the objects we create, whether they're numbers or characters, if they're capable of saving multiple values of the same type of class, and we call that a vector. Okay, definitely not all our objects are vectors, but that's a very powerful thing to have. Someone's drawing on my screen there. Thank you. Let's stop now. Some functions that return vectors. So if you want to create a vector, you basically have to use a function or an operator that produces multiple values and gives them back to you as a vector. So these are some that we saw yesterday. Sequence returns a sequence of integers. rnorm returns normally distributed random numbers. And sample is also another random function. It draws a random sample out of one of the arguments. Okay, so we'll see some more of those today. Another function we saw that can make vectors kind of on the fly is the C function, or it stands for combine. Whatever you put in the parentheses as the arguments, those will become the elements of your vector. Right? So that's very handy. We also saw that you can pull out specific elements of a vector using square brackets. And we see a couple examples of that here. Inside the square brackets, you can either have integers, which represent the indices of the elements you want. So for example, letters 1 to 4, this will give us A, B, C, and D, right? The first 4 letters of the alphabet, because letters is a constant, that is all 26 letters of the alphabet. So you can pass integers and it'll grab the corresponding elements. You can also put inside the square brackets a logical vector, which ideally will be the same length, and this will return the corresponding values where the logical elements are true, right? So these two expressions here are equivalent. They will both give back the first 4 letters of the alphabet, all right? So the square bracket notation. You don't have to remember the details, but just remember, if you want to pull out elements of the vector, you can use square brackets. We also saw that many of the functions in R are ready to go to handle these vector objects. All of the math functions, all of the math operators, you give it a vector and it'll give you back a vector, right? So rounding, cosines, all of the addition and mathematical functions, they're all vectorized. And if you give it two vectors, like if you add two vectors together, it'll add the corresponding elements pairwise. Okay? But we did see there are other types of functions that we're going to call them aggregate functions, and they take a vector of numbers and they give you one thing back. All right, and a lot of the descriptive statistical functions are like that. Right? It's important to remember this because as we get to data analysis, you need both. Okay? Then we also looked at some of the basic plotting functions that come with R that are useful for exploratory data analysis and looking at the distribution of your data. Histograms, box plots, scatter plots, and line points or line plots can be created using the plot functions that you get with R. Today we'll look at ggplot if we have time, which is a more powerful plotting package. But these base ones are, they're good enough to give you an idea of the distribution of your data. All right, so what are we going to do today? For the first half of today, we're going to look at packages, functions, and piping. And we'll do a little exercise. And then the second half, we're actually going to start working with data frames and actually importing some CSV files, which is it's a fairly typical way to import data into R. I do have some slides and some examples of basic plotting. We'll see how far we get along. Okay, so let's talk about packages. Because I made a whole big deal yesterday. You might remember about all the packages that are out there for R, like 22,000 on CRAN and 85,000 on GitHub. So packages are what R calls extensions or add-ons. And they really have made, I think they're largely responsible for why R has really stuck around and in many ways gone viral, particularly in the academic world. So what do you get in a package? The main thing you get in these extensions are going to be additional functions. When you install R, you have there's a few thousand functions at your fingertips, but these packages give you additional packages or different functions that are designed to do specific things. All right? And that's really handy. And we're going to focus on that today. They also force you as a developer, as a package writer, which is not rocket science. Anyone in here could write a package. But if you do submit your package to CRAN or one of those things, they kind of force you to make a help page for it, which is a little bit burdensome, but it's also good because it forces you as a developer to, write what is this argument for? What does this function do? So there are help pages that are part of your packages. Most packages also will have longer form tutorials. They call them vignettes. I think they still call them that. And that explains in more detail how to use the different functions, if it's based on research, what that research is, maybe with but a little bit more introductory material. And then some packages also come with data. Some of them that's primarily or exclusively what they give you. But those in general, those are the things you get in a package. So where do you find them? We saw there's lots and lots of them. This isn't that hard. Talk to people in your field if you're working with other folks. CRAN, which is the nonprofit that kind of organizes our ecosystem, has on their website what they call task views. And they're kind of like annotated bibliographies or reviews. So you can see the different categories. So these are by, sort of domains. For example, there's a task view for agriculture. And this is basically written by somebody who works with agricultural research and knows lots about it, also works with R. And he or she, or it's usually a group of folks, Oh, this one's quite recent. I just updated a couple of weeks ago. But basically, they've kind of list some of the main packages in this domain. And that's, that's one way that it's a head start. All right, so you can find task views can be useful. There is another web page that has all 22,000 packages listed by name. And sometimes I just go there and hit Control F and type in weather or pomology or whatever you might be interested in, Bayesian statistics. A lot of authors, when they're writing a publication, if they've, if they're using R code, they will often publish a package that has the R code for that publication. So that's another place you can find out about packages. And then of course, through the internet, just Google, various people write blog posts, they review packages, they announce packages on Twitter. So all the usual ways that you find out information, okay? So packages. Another thing that R has done really well is they've made it easy to import packages. It's not onerous at all compared to like Python or JavaScript, where you have to do some special thing. So you do need to know what your package you're looking for is, but once you know the name of it, if you're in RStudio, we saw there is a packages tab in that lower right pane. Just click on there, click install, type in the name of the package, and if it's published on CRAN or Bioscience or Biostats, it pops up. Right, so that's easy to do. So installing means you've downloaded it to your computer. That doesn't mean it's ready to start working with. Before you can use the functions or the data in that package, you have to load it into memory. And the way you do that is using the library function, right? And typically at the top of a script, you put in, you load the various packages that you're going to be using into memory using a series of library statements. We'll see that today. Okay, so let's talk a little bit more about functions, because as I was mentioning, that's the main thing you get with packages. So there are 4 things you need to know to tap into the superpowers that you get through R functions. First of all, you need to know what the function is, right? That's not always obvious. Talk a little bit more about how you find out what function to look for, but you do need to know the name of it, in the R case sensitive, so you have to spell it correctly. Then you need to know what are the arguments that it wants. Some of the arguments might be required, others might be optional, which is basically means they have a default value that you can, if you're happy with the default value, you can just exclude that argument. The order that you put them in could be important as well, about why that might be. Then you also need to know, okay, what is it returning? Okay. And we'll see the kinds of things functions can return, but it's a lot. So you have to know what it returns in order to know what to do next. And some functions will also, in addition to returning a value, all functions return values, but some of them in addition to that will do something, such as throw a plot in the plot window, create a file on the disk, and so on and so forth. Okay, so these are the 4 things you need to know about your functions. So what do they return? Well, we've already seen a bunch of functions that return numbers. They can return dates, text, data frames, spatial objects. Some of them will return a plot object, and so on and so forth. I have a package that I wrote that returns I'm calling it a drone image collection metadata record, right? So that's a really specific tailored kind of thing. So almost anything you can think of, or almost anything the package developer can think of, can be returned by a function. All right, so it's not just numbers. It's much more flexible than that. And the other cool thing now is anything that is returned by a function, you can save it to an object and then use it later, reuse it later on. So maybe you don't have to repeat a whole bunch of code all again. All right. So how do you find out what function you know what to use? Well, kind of the same types of sources. Ask your colleagues. You'll pick this up with experience pretty quickly. You can often Google, I want to do a Bayesian hierarchical some flavor of that, and you Google it and you type rstats, and you'll probably find on the first page of search results, somebody's asked the same question. You can find what package and what function you might want to use. But I'm a real big fan, particularly for beginners, of cheat sheets. So this is a great way I find to just kind of learn and familiarize yourself with cheat sheets. And I've linked in three here, which I would recommend for beginners to just take a look at these cheat sheets. So they're PDFs and they're organized pretty nicely. There's a few different ones here, all right? And like this one is dealing with some of the more essential functions or base functions, all right? So that's something you pick up with experience, but there are some resources to help you find functions. Okay. All right, don't see any questions, so I'll keep on going here. So we already worked with functions yesterday quite a bit, right? Like cosine of x, that's a function, right? Anything with parentheses is a function. So I want to talk a little bit though about piping, because that's another way of writing functions, but more specifically, writing a chain of functions or chaining functions together. Because that's a fairly common workflow in R, that you want to put your functions together, right, one after the other. So, and the thing about piping is this might be what we normally would be used to, right? If you worked in Excel, this is fine. This is legitimate syntax, but where you basically nest your functions inside each other, and then R or Excel evaluates them kind of like from the inside out. But that gets clunky after you've done one or two layers of nesting. Piping, which we'll see in a second here, introduces this pipe operator. There's two flavors of that. The traditional one is what I've highlighted here, the percent sign, and then the greater than sign, and then a percent sign, or this pipe character, and then the greater than sign. These are both valid pipe operators. And you can basically use these operators to feed the results of one function into the next. All right, so I think this will become a little clearer with an example. So for example, here we have this kind of ugly nested function. If I wanted to write this exact same thing, but as a pipe expression, I start with what's in the middle. Okay, in this case, it's foo99. These are made up functions. And then the pipe operator. And what that does, it'll then take the result of foo99, whatever that is. Let's say it's 0 or -1. It feeds that into the next function, which in this case is boo, as the first argument. So as long as boo is written in such a way to accept whatever foo is returning, then you're good. And if boo does have extra arguments, you can add them on. And then you just keep on going like that. So in other words, then when you're all done, you get an expression that's more like this. So this reads more like a sentence. Right? It's much more easier to write, to debug, and to understand. All right, and I think we have we'll see. Well, yeah, so that's piping. Here's an example of a real set of piping example where we're chaining together 3 functions using that pipe characters. And what's pretty common also is to use this to break apart a chain of functions across multiple lines. And RStudio makes it easy by automatically doing the indenting. Right, so here we're creating a sequence of numbers from 1 to 10 by every 0.1, taking the log of those, and then taking the sum of the logs, and you get the result. Or some shortcuts for typing in this. To me, this is the only downfall to working with pipes, is like manually typing 3 characters just to get a pipe. But there is a shortcut in RStudio, Control-Shift-M will insert that pipe operator for you. And you can decide whether you want to use the new one, which just started kicking in R4.0, or the traditional one. For today's workshop, I'm using the more traditional one. Probably, yeah, at some point I'll be changing those, but they're equivalent. Okay, let's go to RStudio. I've been talking too long. So go into RStudio Cloud. Okay, go ahead and click on exercise 3.R, and we'll go through that now. Right, let's do the next part. So you probably noticed that you may have noticed when you opened it up that RStudio is giving you a little message saying this script is using a package called agridat, which is not installed. That little yellow button, that little yellow warning message. So let's go ahead and install that package. So you can install it by clicking the install button up in that little warning message, or you can go to the packages tab in RStudio, click on the install button, and then type in the name of the package, which is agridat. All right, and it should autocomplete because this is a package that is on CRAN. All right, and then hit install. And it should just take a few seconds to install. All right. So and once it's installed, you can manually close the little yellow button, the little yellow message. Okay. I'm going to go ahead and also use the broom tool to clean up my environment. Sorry about that. Okay, so you just installed a package. So this RStudio Cloud project already had a whole bunch of packages that I installed on your behalf before I gave you the copy, but now you've seen how to install a package. It's really quite easy. So agridat is an R package. This one's a little bit different, and then it doesn't really have like functions for analysis. It primarily contains data sets. And if you click on lines, first of all, go to line 12 in our script where we are loading the package into memory. And then line 16, that question mark agridat. So the way you get to the help page for a package or a function is you type the question mark and then the name of the package or the name of the function. So agridat is the name of the package. So if you run line 16 by clicking on it and then hitting the run button or control enter to run that line, you'll see in your RStudio right-hand side a help page that describes this package. And this package, it's a whole bunch of data sets from agricultural experiments. And you can read more about who put this together, why they put it together. So we're not actually going to use this package in our exercise, but I wanted to show you an example of a package which is more for data. The help page, if it's too small, this one's probably fine, but sometimes they're really dense. There is a little button on the help toolbar that will pop out the help page in a new window, so you can make it bigger. Okay. But let's go ahead and look at one of the data sets in this package. There's one called Archbold Apple. So the head function, you might remember we did see the head function yesterday. It returns the first 6 elements. And in this case, Archbold Apple is a data frame. So it shows us the first 6 rows of Archbold. Okay, let's keep going. So line 22 here, I'm going to run that. This is using the summary function. And then the argument is this data frame, which is information about Apple, some sort of Apple research. And what the summary function does when you give it a data frame is you may have to expand your console a little bit, but you can see it gives us basic numerical statistics for each of the numerical columns, right? So anyway, it gives you a different, for numerical columns, you get the quantiles. And then for text columns, it shows you like a frequency table. We won't get into those weeds, but that's what the summary command does. Okay, let's go ahead and do challenge number 1. That's where I'm going to pass it over to you. So your job in challenge number 1 is to construct a sequence of numbers from -10 to +10 by 0.2. So the hint is that you can use the sequence function. You may or may not remember what the arguments are for the sequence function. So the second part of the hint is go to the help page for the sequence function. and you should fairly quickly be able to figure out what arguments to pass to generate a sequence of numbers, -10 to +10, where the increment is 0.2. So we're not talking whole numbers here. So to get to the help page, you can type question mark, SEQ, hit enter, and it'll open up for you. Yeah, so the help page for functions generally follows a same template. The top of it gives you hopefully a layman's description of what this function does. And then below that is a section called usage. And sometimes the help page there might be one help page for multiple functions or multiple flavors of a function. But if I look at the help page for the sequence function, I can see the arguments. The first one is from, the second one is to, and then there's another function, and then I can read the other arguments. And if that isn't clear enough, so oftentimes just the name of the argument, you can figure out what its purpose is. But if that's not clear enough, you can read down a little further on the help page, and it'll actually tell you a little bit more information about the argument. So in the case of the sequence function, if I want to go from -10 to +10, then the first argument should be the from, so that's going to be -10. Okay, and then I can put the second argument to, so that's just +10, and then by will be the increment between the numbers, so that's where I put in 0.2, and then I can run enter. All right, so that'll do it for you, and I'll put that in the chat window so folks can see it. Hopefully everybody got that. Now you might be wondering, do I need to name the arguments? So what I mean by that is you can also do it this way. From equals to -10, to equals to, and then by equals to -2. All right. So I'll put this in the chat window as well. All right. So both, what I put it there in the chat window, those are equivalent. The first version, the arguments are not named, okay? They're just listed there. And that works fine, provided that you put the arguments in the order expected, as mentioned on the help page, and you don't skip any, right? So if you're putting in arguments in the order expected and you're not skipping them, you can bypass putting in the names. But if you're not putting them in the same order, or you just want to explicitly put the names of the arguments to help you remember later on, then you need to put in the names, okay? So that's the rule of thumb there. Yes, so arguments that have a default value are optional, right? And if I look at the help page for sequence, all of them have default values. So if I just typed in sequence by itself and hit enter, I don't get an error message. It's not very useful because it's going from 1 to 1, but so I wouldn't, I don't like these default values. They're not useful, but they do have default values. But there are cases where the help page will show you there is no default value for that argument, and that's a required argument. All right, those are great questions. Okay, let's do the next challenge. Construct a sequence of exactly 500 numbers, evenly spaced from 1 to 7. And then once you've done that, verify that it has 500 numbers. Right? So the tip here is you can still use the sequence function for challenge number 2. Different arguments, because here you want to generate a sequence of exactly 500 numbers from 1 to 7. So this is an example where you have to use the sequence function a little bit differently for this challenge. because you're not interested in the interval between the numbers, but you're interested in the total number of numbers. So look at the help page and try to figure out how you can do this. And then once you've done that, maybe save it to a variable and then write another function that will verify that what you've done actually does have 500 numbers. Right? Oh, thank you, Kyle. You found a error in my typo in the code that I put in the chat window. It should be 2 equals 2. Should always run code before I stick it in the chat window. All right, yes, so several people figured it out, right? So the magic argument to use is length.out, and that will compute the interval automatically. All right. Okay, very good. Right? Okay, let's keep going. Okay, well, if anyone wants to do challenge number 3 during the break, we can do that. Okay, let's look at, okay, I'm going to keep going now through the sample script. So let's do a couple examples with piping, and then we'll stop. So suppose this was our workflow. We wanted to generate those 500 numbers, round them to 2 decimal places, sum them up, and then take the square root. This is kind of a silly workflow, but it's not unusual to have a series of functions that you want to chain together. So one way you could do that would be to make each step a separate line, a separate command, and just save the variables and then use the variable in the next line. So that's what's going on in line 59 moving down, right? So the first thing I'm going to do is generate a sequence of numbers. And then the next one, I'm rounding them to 2 decimal places. So x2, that is a vector of 500. x3 is the summation of those. I'm just adding them up. And then x4, I'm taking the square root. And then x4 is my final answer. Right? So that was my goal. All right, so that's an example of doing it step by step. That's not a bad way to do it, particularly as you're getting started or you're trying to figure out, the commands, trying to put them together. We could also put all those together in a single line with using nested parentheses, and that's what you see next. With the square root, parentheses, sum, parentheses, round, parentheses, sequence, parentheses, and then a bunch of parentheses at the end. We get the same answer. So that's the other way of writing it. But with piping, it's a little bit easier to read and to write. So to pipe it, first of all, I have to load a library because I'm using the old style pipe operator. So I load the Magrider library. I can also load the dplyr library that also exports the pipe. And then below that, you can see the equivalent expression, but now we're piping the results of one expression into the next. And you can see with the second one, where we're rounding it to the 2 decimal places, the 2 in there, that's actually the second argument of the round function. Right? So the numbers, the vector of numbers, comes into the round function as the first argument. We can omit that, just assume it's going to be there. And then the second argument for the round function is the number of spaces, the number of places. Okay, any questions? All right, so for you then is challenge number 4, and then we'll take a break. So there's a data set called sunspot type mip. You can just type that at the console if you want to see what it looks like. So I'm going to type sunspot.month, and then hit enter, and you can see it's a bunch of numbers, right? So it's basically, it's the number of sunspots each month since 1750, I believe, okay? So, but it's a set of numbers, right? You can treat it as a set of numbers. And your task is to round these numbers to the nearest integer. I don't know why there's decimal points anyway. I don't know how you can have a fraction of a sunspot, but I could read the help page for this and learn why. and then take the square root of them individually, and then compute the standard deviation. All right, so that's the task for challenge number 4. And when you're done with that, let's take a 5-minute break, come back at 4:25, and we'll look at the answer to this challenge question when we get back from the break. Oh, someone's asking about the challenge 3. Yes, let's do that. All right, so the third challenge. So the third challenge is to simulate 100 rolls of a 6-sided dice and then view the distribution of those 100 rolls with a histogram. So this is a nice little example. So what function have you seen, Gabriel, that could we use to simulate 600 rolls of a dice? Let's start with that. Any thoughts? What function we might want to look at?
Yeah, you can do a sequence with 100 as the length out.
Oh, good guess. Good guess. So sequence will generate a set of integers from 1 to 6. So we could do that, right? Sequence 1 to 6. But that's going to be the same every time, right? So
Oh yeah.
what we really want to do is now we have this set of numbers and we want to pick from them randomly. So the function we can use for that is sample, right? So you might remember sample. I'll do this using pipe syntax. Okay, so the sample function is a function that you can use to kind of like make random selections. Could be letters of the alphabet. In this case, it's 6 numbers. So if I look at the arguments for the sample function, the first one is named X, and that's what I'm picking from, right? So I can use this piping syntax because what I'm sampling from are the numbers 1 through 6. And then the next argument is size. I'll go ahead and name the argument so it's a little clearer. And what do we want? We want 100 samples, right? So we're going to be picking a number at random 100 times. And because we only have 6 and we're picking 100, then we have to sample with replacement. So that's the equivalent of like, you can imagine if there were 6 chips in a bag and you had to pick one, then you'd have to put it back if you want to keep doing that 100 times. All right. So what I've typed here, this will generate that sample. And when I hit enter, you can see down in my console, 100 samples, right? Pick from there. And then if we want to put that into a histogram, I can just pipe that into hist. And the histogram has popped up over there. Okay. Oh, very good. And then we have a, yes, we have an answer for the last challenge. All right. Does that make sense, Gabriel?
Yeah, thank you.
That's doing it as one single expression using pipes. You could break it up as well. Okay, it's 4:25, so I will resume. People are still trickling back, that's fine. But let's finish up and look at the sunspot question. And I am going to put the answer that somebody put into the chat window here. And I'm just going to change it a little bit and make it a piped version, right? Oops. Okay, so we have sunspot month. Let's pipe that into round. That'll take care of the rounding. The argument of round is the number of places. I think the default is 0, but we can just put it there anyway. And then we pipe that into square root. That'll take the square root of those rounded numbers. So now we have, a few thousand rounded numbers, And then we pipe that into SD, which computes the standard deviation. And I'm told the correct answer is 3.2, and yes, that works. All right, so I'll stick this in the chat window. There are other ways you could do it as well. That gives you an example. All right. Okay, very good. Yes, I will share this exercise 3 script with all the answers in it. Okay, let's keep going. Where are we? Break. Okay, so we just saw examples of using functions and using this pipe. We'll be doing pipes a lot more on Friday with data wrangling. That's why I wanted to show them to you. And also on Friday, we'll be now finally working with data frames, because when you're doing analysis, you're probably going to be dealing not with one-dimensional random numbers, but two-dimensional data frames. So data frame is one of 2 classes of data in R that have rows and columns, the other one being matrices. They're pretty much the same. For data analysis, we're mostly using data frames because data frames allow each of the columns can be something different. They can be numbers, some of them can be text, some of them could be dates. With a matrix, they all have to be the same thing. Okay? So depending what field of work you're coming from, rows and columns might be called different things. I think in public health, the rows are often referred to as a case. In the world of GIS, and this is basically an attribute table, the rows are a feature of some sort. Other fields are called records. Your fields could be called a variable. Most generic name is probably field. That's like the columns could be named fields. Oddly enough, though, in machine learning, columns are often called features, but we're not going to go there. But don't be alarmed or confused. I'm going to use rows and columns as the most generic name for rows and columns. All right. But a few key concepts to remember is that every column of your data frame is actually a vector, right? So it's got to have the same class, the same type of thing. All numbers are all text, but the columns can be separate vectors. Something else which is nice about data frames is that your columns can be named, and you can actually refer to them by their name. You can also refer to them by their position, like column number 1, column number 2. So that's allowed as well. But most of the time, we're going to be referring to the columns by their name. And on Friday, we'll see some examples of how you can kind of rename columns if you import something and it's just a god-awful column name. It's relatively easy to change the name to something manageable for your code. Right? If you do want to pull out a single column of numbers, you can just use the $ operator. Right? So there is a data frame called trees. It's kind of like a constant. It's built into R, and we can see it has 3 columns. This is research data from somewhere. The girth, the height, and the volume of trees. And one of the columns is called height. So if we want to pull out just that column of numbers, maybe take the average of it or something else, you can just type the $ operator, the name of the column, and you get back those values. All right. So here's an example where we're doing that, piping that into the summary function, and that's showing us the quantiles of that column. All right. So it's easy to grab individual columns from a data frame with that $ operator. There's a lot more you can and will need to do with data frames in terms of filtering the rows or just getting certain columns. You can do all of that with base R. We're going to use the tidyverse methods, and we're going to do that on Friday. We're not going to go through that today. Right? It's another set of another can of worms. Yeah, but those are some of the things you do with data wrangling: is you subset or you filter or you group the rows and the columns, and that's what we refer to. That's a lot of what we refer to with data wrangling, and that's what we'll cover on Friday. Okay, so let's talk a little bit about how do we get data into R so we can work with it as a data frame. right? So think here, importing a CSV file. All right, it's very, very common. Generally a good idea to make this easier and more robust is to set up your R projects in folders. So this is a little advanced, but people who use R for data analysis often will create a project folder, and then inside that folder, they keep everything together, right? So your data files that you're going to import, such as your CSV files or your spatial data or other kinds of stuff, they're often oftentimes in their own data folder, right? That's trick number one. Trick number two is that in addition to that, if you go into RStudio and you click New Project and you make that folder a project folder, then it'll always, this relationship between the project folder and your scripts and your data will never break. All right, so this is generally the best, a recommended best practice. To do your work in folders, put your scripts in there. So here you can see we have different scripts, these .r files, these are all scripts. Each one of them does something, does a piece of your workflow, a piece of your analysis. And because they're all in the same folder, even if you move this to another directory or you move it somewhere else in your hard drive, or you zip it up and email it to a colleague, as long as everything stays together, nothing ever breaks, all right? Because that's often a pain point when you're importing data. It's just getting your file paths to work, all right? So when you do import data, you do have to give it a file path, right? So here's an example of a file path. This is a file path that could easily break. If I move my project folder somewhere else, or maybe from the C drive to the D drive, it's going to break. So that always works. It's foolproof, but it is fragile. So a better practice is to use what we call relative path names. So here's what I've highlighted here is an example of a relative path to another CSV file. Where we're not starting from C:, or if you're a Mac user, your volume, but we're starting out with the dot. That dot represents your working directory. Okay, I'm covering this kind of quickly, so if some of this doesn't resonate or sink in, don't worry too much. It's helpful, but we'll talk about some workarounds. Something that hangs up Windows people quite a lot is the slashes. So if you are a Windows person, you might be used to working with these backslashes, because that's what you normally see in the Windows environment. R doesn't like backslashes. It actually uses them for different purposes. It uses them to escape characters. So if you're working in R and you're a Windows person, those backslashes, you have to turn them into forward slashes or double backslashes. All right, so that's just a tip for Windows people. Right? When you're typing in a path to your CSV file in your data. Okay, so the working directory, I just made a reference to that. There's always a working directory in R. You may or may not know what it is, but it's always going to be there. If you do want to see what is my working directory, it's often going to be like my documents, depending if you're just like opening up R for the first time. If you do want to see what your working directory is, you can type get wd, and it'll tell you that your working directory. If you want to change it to something else, you can use set wd, right? Or if you don't want to type in this stuff, you can use the RStudio convenience function under the session menu. You can change your working directory. Okay. So the working directory is where file names start from if you're using a relative file name. So, but a lot of that, you don't need to worry about it right now, because RStudio has some features, and this is another reason people like RStudio. So if everything you do in RStudio, if you make it a project, and again, you set the project to the folder where your data are, then when you open up that project, your working directory is that folder, right? So most of this is not a problem. Okay, so that's why projects are good for. But the other thing which RStudio provides that avoids a lot of the pain of finding where your data are is this import data set button on the little tab, the upper right tab. So if you click import data set, it gives you, these are kind of like wizards, like an external data import wizard, like what Excel has. And you just select, are you getting a text file, Excel file, one of these other file types, SPSS, data, and it'll basically walk you through a little wizard where you can pick, find the file, is the first row, the names of the columns, and so on and so forth. All right, so it's a user-friendly little way to import data into R. So you should never have too much pain importing data into R if you use that import data. And then if your data are like it's Google Sheets or a database of some sort, there's a bunch of other packages that you can use to bring it in. So that was a bit of detail on some of the pain points of importing data. So let's go back to RStudio now and actually work with some of this. All right, so go back into RStudio Cloud. If your project went to sleep, wake it up. Okay, let's proceed with exercise 4. So on line 6 of exercise 4, I'm going to import a CSV file using read.csv. That's a function from the base R package. And let me highlight a couple of things here. First of all, I'm saving the results of that to an object called cars_df. So my personal style of naming objects, I will often use underscore at the end of the object name to remind myself what this is. And DF stands for data frame. And if I run cars_df on its own line, I can see that, yes, this is actually a data frame. And when you import a CSV, you get a data frame. That's what read.csv gives you. Also note the argument, what's inside the parentheses for read.csv. It starts out with dot and then /data/stop this cars.csv. So that dot represents the current working directory, which is the project directory. And then the CSV file is in a subfolder or a folder called data. And you can even click on there in the files pane to see what's in there. All right. So that's an example of importing a CSV file. If I was getting weird error messages or couldn't find it, I could again go to the import dataset button and then find it that way. It's a little bit easier. But now we have it in there. So the names function, I'm going to run that next. That gives me the column names of this data frame. There's 4 of them. nrow and ncol, I'm going to run those 2 commands next. As you could probably figure out, they give you the number of rows in this data frame and the number of columns. Okay, so the first challenge is what is the mean of the speed column? So there's a column called speed, and it wants me to know what is the average of it. So that's pretty easy to do. I can simply say cars_df. And then you might remember to grab a column out of a data frame, you put in the $, and then it even will pop up the different column names. And then from there, I can type that into the mean function. Okay. So that's one way to, oops. Okay. So there's a couple of different ways that you could compute the mean for the speed column, but that's an easy one. And I'll leave it to you to, maybe somebody could put the answer to the next part of the challenge into the chat window, right? So do something similar to compute the mean of the reaction distance column. All right, and then put that into the chat window. Oh, okay, thank you. Some people have noticed that pipe operator doesn't work. I should have reminded you to use the library function and load up Margarita. Or if you don't want to use the pipe function, you could just put mean in the cars df. Okay, so the surface column is a character column. And before we go to the surface column, another way that we can view the entire data frame is with the view command. I'm going to put this, I'm going to take this in here. And go ahead and run view. Now this is view with a capital V. And when you run view, so what the view function does is it will open up your data frame in a tab in RStudio, which is kind of looks like, feels like a spreadsheet, right? So you can, there's scroll bars, you can scroll up and down, you can sort the columns, you can apply filters. So the view pane is a good way to preview a data frame. Okay, let's keep going. So compute a frequency table on the surface column. So let's do that together. So we have cars _.df. And then if I look at the surface column, I just look at that by itself, and I can see it looks like it could be wet or dry. If you might, do you remember what function generates the frequency table? If you remembered table, you got it right. So the table will actually generate a frequency table when you give it a vector of discrete values. And in text are discrete values by definition. They're not continuous. Okay, excellent. And then the summary function, as we saw before, the summary function, hit page down. Summary function, you can also use the summary function on a data frame to get a summary of each column, which will either be the quantiles if it's numeric, or a frequency table if it's a character column. Sarah says, isn't piping a bit excessive in this case? Well, that's going to be personal style. Yeah, you have a good point though. Yes, that's a can of worms. When is piping too much? But this is a piping themed session. We'll show you some examples of piping. Okay, let's keep going and do some exploratory plots. So line 39, at least for me, it's line 39. I'm plotting the speed and the braking distance so a scatter plot basically. And we saw examples of basic scatter plotting yesterday. Okay, keep going. Next, we're going to import another CSV, but this one's actually, if you look at the argument for the read.csv file, it's a URL. So this is not on your local computer or your RStudio Cloud project. This is a URL. So go ahead and run that line, read CSV to import animals. And that just shows you that you can import a CSV file from a URL. Not every function that imports data will accept a URL. Read.csv is one of them. Okay, the head function is next. That will show us a preview of this data frame. This is information about animals. Looks like dogs and pigs and cats, perhaps some others. And then we're doing some more summary statistics, computing the mean of the height and weight column. So you might have noticed that the result of the mean function is NA. So question for you might be, well, let's look into that. NA means missing, right? So this is an example where there's some missing data. So let's figure out how could we handle that. So again, the view function, I'm going to run that next, and this is going to open up the animals data frame in a separate tab. And as I scroll down, I can see that there is in fact some rows where the weight is missing, right? Maybe it didn't get recorded or something. So, and the mean function is by default, if you give it a vector that includes NA values, it's going to return NA. So that's the problem we're dealing with. So there's a couple ways that you can deal with that. One would be to exclude those values and then feed it into NA, or there's actually an argument for the mean function that will tell it to ignore the NA values. So that's what I'm going to do next. The next two lines, I can run the next two lines where it's simply telling me how many NA values are present in that column. And then coming down to line 74, we have the mean function again, where there's another argument that's being added that says na.rn. That means remove the NAs and give us back the mean for everything else. All right, so we've just imported a data frame. We looked at some of the columns. We didn't do a whole lot, but we computed some statistics for some of the columns. We're going to do more with data frames, a lot more on Friday. Next, let's look at how you might create a data frame from scratch just with your code. So that's the next section of the exercise. And the first thing we're doing is, for me, this is starting around line 78. We're creating 3 vectors, because you might remember a data frame is simply every column is a vector. So an easy way to make a data frame from scratch with code is to first create the individual columns as vectors. So that's what we're doing, creating a vector of country names, and then a numeric vector called populations, and a numeric vector called area. All right, so this is all fake data. It just illustrates how you could, in code, make a data frame. And then to bring those 3 columns together into a new data frame, that's the next command that I'll run, and you can more or less figure out how this works. We're using the data.frame function, and that accepts the arguments of that should be the columns, and you can even name the columns. So note how in this, I've actually renamed the columns. I'm not using the name of the vector. So I'm saying country equals to countries. So that column will be named country, not countries. Pop equals to populations, and so forth. And then you can view the results. Okay. Next, we verify the number of rows and columns, pull out one of the columns, the population column, and then compute the mean. Okay, then we have that code is all, that's there again, in case you missed it the first time. Okay, 456. So that seems like a good place to stop. We did not get to ggplot. There are some slides on ggplot that we could look at next time, if we have time. So ggplot is a very awesome plotting package that we will try to cover on Friday. All right, so I'll stop there and I'll stay on for a few minutes. People have questions, but we did cover a good bit today. So we back to what we're trying to cover. Yeah, so we talked about packages, functions, using piping, and then importing CSV files and work with data frames. All right, so that's it. Thanks, everybody.